Hello everyone, in this second lesson we will analyze more accurately some controversial aspects of quantum mechanics. In particular we will understand the concept of intrinsic indeterminacy of a physical system, a peculiar aspect of quantum physics. Some uncertainty is present also in classical physics. In fact, because of the limits of our measuring instruments, we can never know exactly the position or the speed of an object. However, in classical physics, we can always try to reduce such uncertainty by using better instruments or observation techniques. Contrary to classical physics, in quantum physics the indeterminacy is not due to an experimental limit, but it is intrinsic to the system itself, and it is neither eliminable nor reducible through the use of more precise instruments. In most situations, in quantum physics, the physical quantities do not have definite values. This does not mean that they actually have definite values but we cannot know them. It means that certain properties do not exist at all, as long as we do not measure them. For instance, a definite position or a definite velocity are not properties of a quantum particle when we are not measuring them. In fact, in the double-slit experiment, in order to generate the interference fringes, the quantum particle must be in different positions and must move in different directions at the same instant. Let's analyze in more detail this intrinsic uncertainty, which is described through a mathematical law called for historical reasons, Heisenberg's uncertainty principle, even if it is actually a mathematical theorem that is demonstrated through the quantum physics formalism. Heisenberg's uncertainty principle can be expressed through a simple mathematical formula, delta x times delta px greater than or equal to h over 4 pi. H is called Planck's constant and it has a tiny numerical value, which order of magnitude is 10 to the power of minus 34 joule times second, while delta x represents the uncertainty in the position. Delta x is calculated as the difference between the maximum and the minimum value of the x-coordinate of the quantum, in case we measured its position. For instance, in the double-slit experiment, the uncertainty in the position of the quantum particle has to be at least equal to the distance between the slits, otherwise the quantum particle could not interact with both slits, and no interference could occur. Delta px represents the uncertainty in momentum, namely the difference between the maximum and the minimum value of the x-component of momentum. Since mass is constant, the uncertainty in momentum implies a corresponding uncertainty in speed. Heisenberg's uncertainty principle indicates that the more precisely determined the position is, the more undetermined the momentum is, and vice versa. How well determined the position is, limits how well determined the momentum can be, and vice versa. To understand better the meaning of Heisenberg's uncertainty principle, let's analyze the following example. Let's imagine a particle closed inside a box. The particle is moving forward and backward, bouncing against the walls. In this case, delta x is the side of the box, since the particle can be in any position inside the box, but it cannot be outside the box. Also the velocity is undetermined because it can have both positive and negative values. The uncertainty in velocity is the difference between the maximum and the minimum value, and then it is twice the magnitude of the particle velocity. According to Heisenberg's uncertainty principle, if we shrank the box, delta x would decrease, and consequently, delta px should increase. Therefore, the particle would move faster and faster. The concept of trajectory implies that the particle has a well-determined value of both position and velocity at all times. The uncertainty principle is then incompatible with the case of a particle moving along a well-determined trajectory. You may wonder why, in the case of macroscopic objects, only well-determined trajectories are observed and no uncertainty principle is applied. The answer is that the very small value of Planck constant means that the uncertainty in speed is completely irrelevant when the mass has the typical values of macroscopic objects. On the contrary, the uncertainty in speed is relevant for subatomic particles because of the tiny value of their mass. Let's try to better understand how the uncertainty in velocity leads to uncertainty in the position, and therefore to the loss of the very concept of trajectory. Let's imagine a car moving at the constant speed of 10 meters per second, and suppose that at the initial instant, the car occupies a well-determined position, that we assume as the origin of the coordinate system. After 1 second, the car will be in a well-determined position, at the distance of 10 meters from the origin. After 2 seconds, the car will be at the distance of 20 meters, and so on. Now let's suppose that the initial position of the car is determined, but its speed is undetermined, and it can be any value between 5 meters per second and 10 meters per second. After 1 second, the position of the car will also be undetermined, because the car can be at any distance between 5 meters and 10 meters from the origin, therefore, delta x will be 5 meters. After 2 seconds, the uncertainty in the position will have increased to 10 meters, and so on. The uncertainty in the velocity implies an uncertainty in the position, that increases proportionally to the time. Let's try to apply Heisenberg's uncertainty principle to a macroscopic object. Let's suppose that the uncertainty in the positions of the object is very small, equal to the inner atomic distance, namely delta x equal to 10 to the power of minus 10 meters. By using Heisenberg's formula, we can calculate the minimum uncertainty in momentum, which becomes 10 to the power of minus 24 kilograms per meter over second. Let's suppose that the mass of the object is equal to 1 kilogram. In this case, the uncertainty in its speed would be 10 to the power of minus 24 meters per second. From the equation of the uniform motion, we can easily calculate the time lapse required for this 1 kilogram mass to delocalize by 1 millimeter. Solving the equation, we find that such time lapse is about 10 to the power of 13 years. This time lapse is about 1,000 times larger than the age of the universe. This makes us understand why macroscopic objects, although they are only aggregates of quanta, always move along well-defined trajectories. Our observation time will always be too short for the effects of Heisenberg's uncertainty principle to be detected. Therefore, it is not true that quantum physics is not valid in the case of macroscopic objects, as we often read or hear. Quantum mechanics is a very general theory, and it is valid for both microscopic and macroscopic systems. However, since classical physics is much simpler, it would not make sense to use quantum physics to describe the dynamics of macroscopic objects, since the quantum effects in their case are too small to be observed. If we repeat the previous calculation for an electron instead of a macroscopic object, we find a minimum uncertainty in velocity equal to 10 to the power of 6 meters per second. Therefore, after 1 second, the electron is already delocalized over a distance of 1,000 kilometers. This means that if we closed an electron in a box the size of an atom, and then we open the box, the electron would lose immediately its identity as localized particle. However, it must be clear that the analyzed example refers to a free particle, namely a particle not subject to any forces. On the contrary, in the case the electron was close to an atomic nucleus, because of the attractive electric force, it would remain in vicinity of the nucleus. However, the electron would be in a delocalized state. It is then wrong to imagine atoms as if they were miniature solar systems with particles orbiting around the nucleus. Actually, it is precisely the delocalized nature of the wave function of the valence electrons that generates the chemical bond. For example, in the case of a macroscopic piece of metal, the wave function of valence electrons is delocalized over the entire block of metal. But how is a system of delocalized quanta with indeterminate properties described in practice? This is what we will now try to understand. In classical physics, a system is described as a set of particles that occupy a well-determined position, and have a well-determined velocity at all times. The laws of physics determine the evolution of the system, namely how positions and velocities change over time, regardless of whether the system is observed or not. The evolution of the system is absolutely deterministic, which means that it is uniquely determined. In quantum physics, the concept of particle is no longer adequate to describe the system, because quanta do not occupy generally a well-determined position. So, a totally different approach is necessary to describe a quantum system. The system is described through a mathematical function called the wave function, and what evolves deterministically is no longer the physical system, but only the wave function. It is important to stress that the wave function, however, does not represent any physical property of the system, but it is only a mathematical tool with which we can calculate the probability distribution, relative to any observable property of the system, if we measure it. In particular, the wave function provides the probability of finding the quantum in a given position. To understand how this wave function method works, let's assume we use quantum mechanics to describe the motion of a macroscopic object. In this case, the wave function would give us, at all times, only one possible position with 100% probability, and 0 probability for all other positions. A graphical representation of such wave function would contain only a narrow peak, as it is shown in the figure on the left, and this peak would move over time, according to the classical equation of motion. The graphical representation of a wave function describing a partially delocalized quantum would be more flattened, like the one in the figure on the right. In this image, we see instead an example of a wave function describing a totally delocalized quantum, because it is not possible to attribute to it, even approximately, neither a position nor a trajectory. The fact that there are more peaks shouldn't suggest that there are more particles. These are peaks in the probability of finding the quantum, that always remains only one. The Schrödinger equation allows us to calculate exactly how the wave function changes over time. In cases where the wave function has a single localized peak moving regularly in space, the quantum behaves similarly to a particle moving along a trajectory. On the other hand, when the wave function has more peaks that rise and fall irregularly, then the quantum is no longer comparable to a particle. So let's look at the graphical representations of some exact solutions of the Schrödinger equation, that show the evolution over time of the wave function in some simple cases. We begin with the wave function of a quantum stationary in the center of a box, which for simplicity, we assume to be one-dimensional. You see that initially, the probability of finding the quantum is maximum in the center, but since the speed is indeterminate, the wave function must change over time, and in fact it changes to represent something that is delocalized in the whole box, like an oscillating standing wave. The peaks of the standing wave represent the positions where the probability of finding the quantum is highest. In this situation, the quantum has lost its identity as a particle, as there is no longer a single localized peak, and it is not possible to identify a trajectory. The next simulation refers to a quantum closed in a two-dimensional box. In this case, the different color gradations are used to indicate the areas where the wave function assumes higher or lower values. Also in this case, the initial wave function is localized, but over time it delocalizes, until it extends to the entire surface of the box, presenting the classic maximum and minimum interference fringes. Now let's look at another two-dimensional simulation, with different parameters, so that delocalization is faster. It is evident that already after the first bounce, every trace of trajectory in the motion of the quantum is lost. This is the simulation of a quantum moving towards a small obstacle. Being the obstacle small, the probability that the particle bounces backwards is very low. Surprisingly, there is a central peak, which represents a relatively high probability that the quantum passes through the obstacle, as if the obstacle were not present. It's called the tunnel effect, and it's a typical quantum effect. Also note the presence of various peaks due to the interference of the wave function with itself. In the next simulation we try to better understand the tunnel effect, which represents the possibility for a particle to cross a barrier. It is a typically quantum effect, because in the case of macroscopic bodies, either the body breaks the barrier or bounces backwards. Here we see a quantum moving against a barrier. You see there are two possible cases. The quantum has about 40% chance of crossing the barrier and 60% chance of bouncing back. It must be understood that the quantum has not split into two parts. If we put a detector, we will always find it in one piece, either on one side or the other. It is only the wave function that has split to represent these two possibilities. The wave function is just a mathematical tool that allows us to calculate the probability of finding the particle in a certain position, if we look for it in that position. In this last simulation, we see the graphical representation of the wave function of a quantum, heading towards a barrier with a double slit. To the right of the barrier, you see the maxima and minima of interference. To the left, you see the probability that the particle bounces backwards. Well, these simulations should have helped us to understand what is meant by uncertainty in quantum physics and to get an idea of the meaning of the wave function and delocalized state of a quantum. But the question that now arises spontaneously is, what happens when we measure a property and find a specific value? In fact, the property can no longer be indeterminate since we have measured it. This is the central problem of quantum physics, as it is precisely this aspect that has raised profound philosophical questions and has challenged the common idea of the objective existence of reality. We will address this in depth in the next lesson, where we will also discuss Schrödinger's famous cat paradox, which was devised to highlight the extremely problematic conceptual implications of quantum physics.